So counterfactuals, the first credit, right? So those slides are mostly done by my PhD Maximilian, who's currently doing a really exciting internship um, that we're not talking about. But yeah, so like a lot of the props for the slides goes to him, right? Um, so counterfactuals kind of answer the question, or in general, the question of counterfactuals, as like also for like in a common tongue is basically what if, right? So what would happen if, what about y if x, right? These kind of things. So for instance, in this Disney series, right? So we have like in the main timeline, let's say, we have Steve Rogers getting the super soldier serum, right, and becoming Captain America. Amazing, right? And but what would happen if actually something went terribly wrong? The whole like super soldier serum thing went awkward, exploded, Steve Rogers died, nothing ever really happened, right? So what would we end up with? Like no Captain America means Hydra takes over, means we all are fascists, right? So that wouldn't be great. But luckily, there's like another solution coming out, right? So like in this, like Major Carter basically steps up and becomes Captain Britain in this case, right? But she's basically here to save the day, right? Like so that's basically all counterfactual. What would happen if the super soldier serum experiment would have gone wrong in the US, right? So what would Y look like if X happened, right? So like explosion in the lab, what would our current day be, right? So what would Y be if X would be different? That's kind of like the general understanding of what a counterfactual is, right? And with this, basically with this general understanding, unfortunately, or like fortunately, or whatever, that is not quite the case in how we define it mathematically, or like in the context of explanations. We'll come to this in a second. So let's start right away into the multiverse of counterfactuals, right? So again, counterfactuals like seem to be very related to causality, right? But in our community, causality and causal ML are separate from that. So let's talk about this for a second, right? So let's assume that something goes horribly wrong, right? And like we have to move the lecture, right? So like something went bad, and like or like in the factory our sales break down, right? Something like this. So now what we see or what we observe at the same time is like an email going out like, hey, there's like water down, or there like you cannot come to the lecture room anymore, right? And then we have to move our lecture. So we might actually correlate those things. So we might actually think, okay, the reason why we cannot be in the lecture is because, like in our old lecture room, is because of the email that went out, right? So because of the alert that we got. But in fact, like in reality, there's something causing both, right? There's something that happened that caused the emails going out and us not being able to be in our old lecture room, right? So, and even further, there might be something causing that, right? So the water damage or whatever might have caused by like evil students or professors, not taking any blame here, or like some bad weather or just like some other environmental problems, right? So you can see like this causal chain can become bigger and bigger and bigger. And in general, the question now is at which point is it causality and which point is it correlation, right? So like the pipe burst, right, might be like just correlated to the other effects, right? But not necessarily caused by the other effects, right? So there might be evil professors in the building just at the same time as the pipe bursted, right? So we don't really know. So to quote like our dear colleague Francois Chollet, like he's at Google currently, he's a French computer scientist, right? Causation causes correlation, and correlation is correlated with causation. And that is it about causal ML, right? So you can see it's actually quite complicated, and there's a lot of works like double ML and so on that try to basically figure out how this causal relations actually happen and how to deal with this. And in fact, there's unfortunately, from personal experience, a discrepancy between, let's say, the mathematical community, how they deal with causality, right? So like we have like Judea Pearl, who does like amazing research in this direction, but it becomes completely untractable, completely uncomputable for us. And the, let's say, robot or machine learning community that wants to do something practical and then makes like assumptions, approximations, and the mathematicians are like, no, your approximations are bad, and then it becomes very hard to work together, right? So, anyways, if we look now again, what would Y be if X would be different, right? So we basically put this a step back and try to tackle something more like tangible, right? So like a formulation that is more like solvable for us. And the question becomes now, given X and Y, right? So given like our input and our output, if we want a different Y, what would the different X have to look like, right? So instead of just like predicting the future or like whatever the other thing could be, right? We actually simplify our problem and look at it slightly different. And say like, no, we know that we want to have like Captain Carter or Major Carter, right? On the shield. What would we have to change now for this to happen, right? We need to rig the lab or something like this, right? So we need to do something. So again, in this case, it's not just like any Y, but we have a particular desired like output in mind that we want to have, and we kind of want to figure out what the necessary input for that would have to be, right? Does this make sense? And this becomes like much more tangible right away, right? So why is this a simple problem? In your own words.
Because you have to be a goal.
Yeah. So because we basically know where we want to end up. Grab a chair. There are chairs like somewhere in the back. Lose the iPad. Okay, so that brings us to counterfactuals, right? So again, in counterfactuals, we don't try to solve the entire causal chain, right, or anything in this regard, but we rather want to see like, okay, if we have all our different inputs, right, and something bad happens, or like, or in general, something happens, but we want it to be different. What do the different inputs have to look like, right? So if we want to go our sales to go up, or if we wanted to stay in our lecture room, right? What would the other inputs be like? So for instance, if there wouldn't have been an email coming, right? Would that allow us to stay, right? Or is there like other things that would have had to change? Does it make sense? And then of course now it can be that there are some other things that can change, right? So let's say like just not having an email, right, telling us to get out of there, right, is kind of like a good indication that we can stay in there, right? But also just not having the pipe burst would be an even better indication, right? So there's different ways that we can like stay in there. So one way to deal with this ambiguity, or different. Let me ask you, what do you think? Like, how can we deal with this now, with this ambiguity?
You keep on observing and try to model it. For example, with a PDA.
But what would this help us if we just if we're like, yeah, if we're interested in a good solution, right? And we have infinite many solutions. So we would model all the infinite solutions and then have a model over the different solutions.
You would first observe how the world works, then build a model, then compute what the distribution in a sense in X would be for a given Y, and then we would choose one of the most probable X to cause the Y.
What is so the most probable X, right? So so the X that you're looking for is the most probable one in your case.
Y with the highest probability, then yes.
But do you think like just observing those different X's, right, would be sufficient to model or to learn a model that tells you how probable any of those X's is?
Possibly. Depends on the environment and on the specific problem.
Maybe, but like I would guess in general. Plus, you would have to basically solve this like I think that will be computationally quite challenging. And for a like just for the end that like we want to have the most probable X, right? But do we actually care about the most probable X? So is this the metric that we like who thinks that the metric that we're trying to solve is the most probable X? Like that gets us to our to our Y dash. Yeah.
I didn't mean the probable X as the most probable X to occur, but the X that causes the Y dash with the highest probability.
Mm-hmm.
In systems, you often don't have determinism. So even if you know
In classifiers, you do. Like most classifiers are pretty deterministic. Language models are pretty much deterministic. Like a lot of predictors are deterministic. We live in a deterministic world, right? With like a lack of information, which we approximate through stochasticity, the stochastics, right? But in general, like things are deterministic. And don't start with quantum realms, right? Like so, even there, the jury's still out, right? But yeah, so I'm a Einsteinian, as you can figure. But anyways, no, but this is a good idea. But still, nevertheless, are we looking for the x that will most probable, or the x dash that will most probable cause y dash? Is that our metric that we're trying to optimize? Because if I kind of just find one that does cause y dash, right? So because like I'm treating this as a deterministic problem, right? And there is multiple x dashes that cause y dash, right? So what is the metric that I'm optimizing? What would be a good metric to optimize?
Like maybe you could like if we, for example, talk about images, maybe we just want to have an image that is maximally different from the original image, just that we can like use some distance metric and get some images that are different. Although that might not be a good idea because then you might get noise.
Most likely you will.
Yeah, that's not a good idea.
I think you were first.
So if we had control over the input variables, the axis,
We do.
for example, the water damage.
Yeah.
Then we could increase the water damage or decrease the water damage and look how it changes the outcome. And we keep all other variables the same. And then we do that for all other variables, like we send 2 emails or no email. And look how the output changes.
It starts to look sound a lot like Shapley values, right? So like that basically will lead us down a computational rabbit hole, right? Like so like something that isn't great either, right? But it goes in the right direction. So like again, it's up to you what metric you choose, right? But the argument is that the like if I kind of let's think about it in a personal way, right? Like so I have certain properties about myself, right? And I want to change some y, right? So let's say I want full hair. No, that's not gonna happen. But let's say like I wanna be fitter, right? Like I wanna like be able to walk up the stairs here if the elevator is broken without grasping for air or something like this, right? There's certain things that I can change about myself, right? Different properties, right? That like will lead me there. But do I want the one that like guarantees me that I always be there? Do I want to like do all of this, or do I kind of want to go minimal effort and see what is the least thing I can change about myself to achieve my goal, right? So chances are like a good like approach here is to see that we're trying to make the minimal changes to the existing world, right? To the existing properties, because I could say like, okay, in order for me to be up here, right, like without any issues with the stairs and so on, I should like exercise more. I should never had like leg injuries. I should like not be asthmatic and like these kind of things. But all of these, some of these features I can control and some I cannot. So some of those settings are unrealistic, right? So if I basically say like, okay, I want to see what is the smallest change to the X that exists already, right? I try, or the hope is that I stay within the more realistic realm, right? Within the more within the domain that is achievable. Does it make sense? So our metric is actually like a good counterfactual or a counterfactual explanation of a prediction describes the smallest change to the feature values that change the prediction to the predefined output, right? So that is what we're looking for. So not the most probable, right? If we would be in the stochastic domain, not the most different, right? But the one where everything stays like as close as possible to what already exists, right? In the sense that like, or with the hope that we still stay within the domain of the model, right? Because that's the other thing. If I change something completely, I don't even know if the model knows how to deal with this.
I always get confused by these explanations because it sounds very much like an adversarial example to me, like the minimal smallest change to a feature value that changes the predefined output. Wouldn't it make sense to maybe like introduce something like actionable, like we need to differentiate between an adversarial example and an actual sample that is achievable by normal means, if you know what I mean. For counterfactual. Like we don't want.
I don't
to
understand what you
change-
mean by achievable by normal means.
Yeah,
like
for example-
just an adversarial example doesn't mean that it's not achievable.
Yeah, I know, but like let's, for example, you want to make a counterfactual for the set of A data set or something.
Yeah.
You want to change the hair color. You can basically achieve a different output by an adversarial example by changing random stuff in the image that is not noticeable, which would basically be a small change.
Mhm.
Or you could adhere to the data manifold, if you know what I mean, in the set of A and change, for example, the hair color.
Mhm.
So what is like in literature, what is really a counterfactual in this sense? Is an adversarial example a counterfactual essentially?
We actually have a slide for that towards the end. So like remember that question, right? But in general, there like just because we're trying to create a counterfactual doesn't mean that we have to leave the robust possibilities, right? So if, for instance, some of your features are categorical, right? You just choose other features or like instances that are within that category, like within the categorical distribution, right? Like you don't actually choose a completely new category that you never had, right? So and it might be that there is no good solution also, right? So that can also happen. Yeah, but like with the adversarial, they're very connected, right? Like, and we're going to talk about this, or like just briefly mention it towards the end, right? Yeah, so how can we actually solve this whole, like, first, real quick, like, does everybody get this? Right? So for instance, in this case, why this would be like a better counterfactual than the top one, because over here, we basically just reduced the damage a little bit, and on the top, we chose like other features that changed significantly, but still would lead to the same outcome.
What if there are multiple smaller changes that lead to the same predefined output?
Very good question. That can, depending on how you like get to like, so this would be again something where I would distinguish between what our goal is, right? Like what the model would be like, or what the output would be like. So the features and how we get there. So like the algorithmic differences. So depending on what algorithm you choose to get there, you might actually end up with always only one solution, right? And potentially have things like mode averaging and these kind of things. Or you actually might end up with like alternative or like parallel explanations, right? But then like that can happen, yes. And then you figure out how to deal with it, and or like as a human.
Would the goal here be to use our distribution images to do that, or to try and reduce images that possibly be actually hard?
I don't think as much in terms of images here, right? But in terms of like the features in general, I don't think like it makes like it's necessary to go out of distribution, right? So instead, I would rather think about like the adversarial like pipeline where you try to still have something that is at least like somewhere reasonable within the distribution, right? But it can very well be that you end up with like depending on again how you approach this problem, right? So how you generate your counterfactuals, right? You might end up similar as we did with like the feature permutation and so on with like Frankenstein samples, and that by definition would be out of distribution. It's not a very satisfying answer, but do you get it? Okay, cool. Yes. Okay, so now the question: how do we actually like go about this to solve this? And like we're gonna look at this as a optimization problem. So proposed by Van der Wachter et al. in 2017, right? So we basically just formulated as a loss for now, right? And the idea of the loss, the parts of the losses are that we have our true data point, so our original data point, right? And we have our desired target where we want to be, y dash, right? And we have, of course, our counterfactual example, right? So which will be x dash and some weighting term lambda. The weighting term basically weights the black box model output. Again, in this formulation, there is no hat, but imagine there would be one, right? So in this slide deck, F just in general means the black box model or the complex model, right? Like usually, as I mentioned yesterday, I always have the hat on top. That's not here the case, right? But still, this is F hat from yesterday. Make sense? Okay. So, right, so and we basically input our like whatever our x dash could be, right, and see if the output matches what we want the output to be, right? So our y dash, and then in addition, we basically have our feature distance, and the feature distance we're going to talk about in a second now, right? So, any question about this loss so far? Basically, just like normal vanilla MSE loss in this case, but you could also like imagine other like distance losses or distance metrics, right? So, right? So all good. And the weighting term, of course, basically tries to find like a good, in this case, parameterized like equilibrium between those different terms, right? So our distance term, right, or feature distance consists of two parts. Like on over here we have the Manhattan distance simply, right? So why the Manhattan distance? Because the idea is that if we only ever subtract like or compute the difference between the features without actually squaring them, we get a more intuitive explanation afterwards. The counterfactual will be, or the different parts of a feature vector will less affect each other during the optimization, right? So we actually try to play with individual features, right? And on the bottom, we have our median absolute distance. So let me elaborate on this one. So our median absolute distance, right? So absolute, and this is the notation for the median, right? So in contrast to the mean, right? So there's this 1/2 on the bottom seems a bit weird, but it's basically because the median is in the center, right, of our sorted like potential values. So yeah, so that's the definition here. So why do we actually use this as a normalizer? Because the idea is that this kind of approximates a normalization by variance, right? And kind of like equalizes the different units in the sense that like if they have like different, like significantly different domains that they live in, right? So we kind of have this averaging that they pulled back into the single domain so that during the optimization, none of the individual feature elements gets like dominance, right? Okay. So yeah, smart. So in general, the intuition here is also that it's it seems to be also more robust, or like the idea is that it's more robust towards outliers compared to the plane variance. So it's kind of like almost like the standard deviation, but not quite, because instead of the mean, we're using the median here. Okay. So with this loss now, so how do we actually optimize it? So you notice that like the big question is what happens with lambda. So we have a trade-off between the hitting target, like right, so like the finding our desired outcome and minimizing the distance of b0, right? And in practice, it's just difficult to find good examples for this. But what we can do always, or like question to you, what would we do in these type of cases?
Like we would just try out many different lambdas and see which one is best.
What would we do if we like ourselves and don't want to punish ourselves with these type of tasks? And we don't have access to amazing students and do gradient descent on students, right? So, well, this is like a clear case for a constraint optimization problem, right? We want to solve one part of the equation while maintaining another one, right? Make sense? So what we constrain here in this case is basically the distance, and we want to make sure that this distance is always smaller than some additional threshold epsilon, right? And then basically by formulating like this, lambda might fall out or will fall out like as for instance, a Lagrangian parameter if you do Lagrangian optimization or something like this, right? In order to deal with the constraint optimization problem. Okay, so any question about this step? So this is basically the first approach how to deal with this, right? So we basically have our loss, right? And the only thing that we want to, or the thing that we want to do is basically match our like target while like still like kind of maintaining this feature distance to the original feature point, right? In order to, because as we mentioned, we want it to be as close as possible to the original feature vector in this case, right? Okay, cool. So this seems to be clear enough for everybody, right? Okay, so while that is nice and everything, we actually haven't talked about like what makes a good counterfactual explanation, right? So we said that we want it to be close, but is there other properties that it has to fulfill, right? So let's start with like the prediction has to be close to the target, which is obvious. Right? So we kind of like that makes sense because if it isn't like the prediction on the counterfactual, then it's pointless, right? Then we want it to be close to the original data point. We discussed this about this too, right? So, but like something that we haven't mentioned is that we also want to have sparsity. So as we already talked yesterday when we talked about the L1 regularization and so on, sparsity usually leaves like or gives us better solutions, right? So think about Occam's razor, right? So the solution with the minimal change and so on, right, or the most like is the most likely one, right? So in this case, if we have only like sparse changes, right, like or there's like only like individual differences to the data point, right, or small, then this is what we kind of want to have, right? And the last part is that we want to have likely features. Likely features meaning something within the distribution, right? So features or feature values that have been observed somewhere in our overall distribution. Make sense? So I think like all of those four, like those were proposed also by Molnar, or like actually by Dandel et al. With Molnar being called for on this paper, right? Christoph Molnar, the person that we talked about before, that did this amazing ebook. Exactly. So yeah, so I think all of those, like, are those clear? Why we want to have those, right? Okay, nice. Okay, so then basically look what our loss looks like now is a multi-objective loss. So we have different parts of this loss. I don't say terms intentionally, right? So we have different parts of this loss or different objectives in our multi-objective part. The first one basically being our target loss, right? Then we have the closeness loss, we have the sparseness loss, and then finally we have the likeliness loss. Don't confuse likeliness with likelihood. Those are different things, right? That's important. So if you afterwards start Googling, right, like don't assume this to be a likelihood loss. It's not, right? So let's start with our target loss. So again, what is the purpose here? The purpose is that the prediction of our counterfactual should be as close as possible to the desired prediction. I think that is obvious. That makes sense, right? So we can simply have like some kind of distance loss. Again, here we take the absolute distance, right, between the produced output and our desired output, right? That makes sense. So I don't think that there's any dispute or like question about this one, right? And of course, like if we want to do this for multiple counterfactuals, we want to do this for every element of the feature vector, right? So here's basically J is indexing the different features, right? Or the output actually, rather the output dimensions. So the next one for the closeness, our counterfactual should be as similar as possible to our original or the given instance, like feature or like no features, but like input instance, right? So we do this again through like some distance measure where we say like, okay, we get our x for each individual feature, we get our x dash and like our original x, right? And then we can use something called the goer distance, right? Which will always normalize between 0 and 1, which is very nice for like different or for stability reasons of this objective, as we will see in a second, right? But yeah, and the idea is that, or the cool thing here, that we can also use this for continuous values as well as categorical values, right? So I mean, I can go through the equation, but I think it's pretty much clear what it does, right? Like so. Okay. Finally, the next term, or like no, finally, but the next term would be the sparseness, right? So our counterfactual should produce the desired prediction with as few changes to the original as possible, right? Does it make sense? You don't seem to agree, or like what do you find interesting about this? Okay. I always like when I see smiling students, right? That makes me happy, and I want to see what they share, or like what they see. Okay, yeah. So basically, this one literally just yes. I mean, it's not a norm. I know. I didn't make the equation, so the zero norm is not the norm. I agree, right? But generally, the idea is that like what are that we want to have as few changes there as possible, right? So we're going to have as few instances where the xj and x dash j are not equal as possible, right? Make sense? Okay. And then finally, like for the likeliness, our counterfactual should have likely combinations of features, right? So the idea here is that we have something like a k-nearest neighbor loss, where we see like, okay, if we have now our generated like new feature, like how many, or how close is it to the k-nearest neighbors, right? So we want to minimize that thing too, or that distance. Okay. Any questions about this so far? Make sense?
The loss now is a tuple.
Hmm?
The loss now is a tuple of a number.
It's a quadruple.
Yeah.
Yes.
And also need to have the weighting terms for each of those.
Oh, very good question. So how do we optimize this? Right? So like we can introduce weighting. What is the problem with, well, okay, try to not look at the at the text bullet points, but what is the problem by just introducing weighting? By just making it an additive loss? What will we lose?
Generality.
In what sense? General, like the answer was generality. In what sense?
It might be different. It might need, you have to do tuning of the hyperparameters, which always introduces new work. And for different problems, these hyperparameters might have to be tuned in different ways to work more effectively. So what you could do is do a multiplicative loss or a log loss, but the problem then which can occur is that you have instability in the loss with a multiplicative loss.
Even if you don't have instability, what will certainly not be the case? Like so sorry, if like okay, even if we don't have stability, comma, what will be like the most likely let's say manifold of this loss, right? It won't be like there won't be a global like easily, it won't be convex, right? That's what I'm trying to say. So there won't be like one solution that satisfies all four of these terms. So even if we weight that, right, there will be trade-off between the different terms, which means that like some of them actually like might be like ignored, right? So like it becomes very sensitive to the weighting itself, right? So and then that's kind of like what we don't really want. So instead, what we could do is optimize all four of those at the same time, right? So instead of having like a weighted term, we basically go with like for instance, a different type of optimization, right? Not a gradient-based optimization that allows us to just play around, like trial and error, right? So we try different values, like for our X dash, right, and see how fit the overall like or like I already gave it away, but how good it still performs, right? Like so how close we are to the loss, and we kind of do this in a structured way, right? Similar to like evolution, right? So like that kind of gives away the idea. So what can we do? How do we optimize this? So instead of going a gradient-based route, we actually optimize this through genetic algorithms, right? So the idea here is basically that you start with like your initial population, right? Like you randomize it a little bit, and then or like your initial guess, you randomize it a little bit, and then you basically start combining those different feature aspects, right? Like you combine them, then you slightly change them, like the mutation part. We do the selection step, which is basically like assuming or computing the fitness. I don't know, are evolutionary strategies or genetic algorithms still taught? No? Okay, so don't sweat it. It's not important for the exam, right? So just like it's important that it's not a gradient-based approach as we do here, but like a evolution-based or like a genetic algorithm. Mhm.
For the fitness, you still need to make different terms of the loss.
Not necessarily. You can have like if one of those terms is not followed properly, you're unfit. It doesn't like so basically all of them have to be achieved to a certain degree, right? So like there's no one term that outweighs another one. So if I have a significant shortcoming in one of these losses, there is no value for any of the other losses that will make up for it.
Okay, so you could have so if one was decent at 4 and one was a bit worse at 1, but a lot better at another, then the one that would be better on average would be better.
No, like I mean, if you're not fit, you're not fit, right? Like so basically, like if my different losses are basically my four extremities, right? And if any of them is missing, that one is missing, right? So like it doesn't matter if the other one is much stronger.
If both are I mean, you have to set a certain threshold, right?
Yes, but that depends only on the term itself. It doesn't depend on the overall loss term, but on the individual ones. Right? So there's no compensation. That's what's happening. Right? Does it make sense? No? Okay. And that's basically the big benefit of this guy. Of course, that thing is like there's questions about convergence, there's questions about like actually finding like good solutions in a reasonable time. So there's computational complexity, these kind of things. So this is by far not perfect. The actual genetic algorithm used here is called non-dominated sorting genetic algorithm, right? And the non-dominated sorting already points you towards the idea that there's no individual term that dominates, right? The loss at all. But like we're not going to talk about this as a whole. But that gives you basically the idea how to optimize for this in general without having to go down this compensation route. So with this, the cool thing about this entire approach, like including the genetic algorithm, there's no hyperparameters, which is not completely true, right? So there's like these thresholds that we might have to set and these kind of things, but it's like not like, yeah, it's fairly easy to set the parameters. Let's put it this way, right? But we have to deal with a genetic algorithm, which, like computational complexities and so on, like non-guaranteed convergence, these kind of problems, right? On the plus side, again, we actually get multiple diverse solutions. So there was a question prior, what happens, or can we actually have multiple solutions? Now we can, right? So we have like very diverse solutions that don't depend on each other at all, right? But at the same time, we have what is called the Rashomon effect, right? And the Rashomon, like who knows, who is a cinephile and knows about Rashomon? Nobody here? Okay, cool. So Rashomon is a Japanese movie from the 1950s, and it's credited to as the first movie ever without a consistent or reliable narration, right? So you actually see the same scene playing out, or the same problem playing out in 4 different ways with 4 different narrators, right? And each of those narrators actually believes the truth, right? Like, so they kind of like talk in their own favor, but none of them like intentionally deceives and lies, right? So like now you have like 4 contradicting truths, right? Which kind of is a big issue, right? And this was the first movie that actually like tackled that. And a little bit of trivia, as far as I understand, is that the editor that basically cut all of this together afterwards quit and never did the movie again, right? So they were like, okay, this is nonsense. I'm done, right? So that part. But what this means also for us is that we can have contradictory explanations, right? So for instance, there's some data sets where people like did experiments on, and for instance, if I want to have my loan approved, right? So there's one solution that actually will get me the loan approved with the current model at hand, right? The one that I'm analyzing. If I'm 5 years younger and I'm asking for less money, right? But at the same time, there's another solution which wants me to be 5 years older and ask for more money. Why the bank or the model would do this, that's not the question here, right? So the question is basically what would be, what would I have to change about myself in order to get the loan approved, right? And those are contradictory examples. And usually this is referred to as the Rashomon effect. Okay, so questions about this?
Is this example contradictory or bank, for example?
Well, you cannot contradictory in the way that you can combine those 2 results, right? So like you cannot pick it has to be either or, right? And this is good. Yeah, good question. Okay, cool. So now let's get to the advantages, advantages of counterfactuals, right? So we have like a clear interpretation. So the examples are very intuitive, right? Because we can see the features directly, which is really, really great. It works on like just input and output. So we basically don't need like in the example that we gave as the last method, right? We don't actually need like gradients or anything like this, right? So it works completely like without this additional model knowledge, right? Here we say proprietary data set. What we mean is explicit data set. So we don't need to have like an explicit data set that we need to manipulate and so on. Like for instance, we do in SHAP, right? Like this is another big benefit. Like the web API is kind of like, yeah, so forget about that. But the idea there is basically that you don't need that much in terms of like algorithmic infrastructure necessarily. You could potentially even query people, right? So you could ask like, okay, so what would you change now as a feature if you want to have this output, right? And then you try it out. So like kind of this, but forget about that argument, right? So Paul, maybe also we scratch that for the future. The last one, the naive API, the web API, right? And yeah, and like the implementation again is fairly straightforward, right? And like the losses are very intuitive, very easily to parse. Okay. So any questions about like this type of counterfactual before we go to something more recent? Okay, so something recent now, like a paper from last year by Wu et al. Basically tries to answer if LLMs do actual reasoning or they just reciting, right? And this is, I think, like a question that is like in everybody's mind, right? So it's very important. So yeah, so the question is like, are they basically just like very good lookup tables for the next possible word, right? Or is there actually some understanding, like concept understanding and argumentation inside of the LLMs? And that kind of reminds like me and also Max of the Chinese room problem. Who has heard about this thought experiment? Okay, so not that many actually. Interesting. I still learned this in my AI lecture back in 2014. But yeah, I think much cooler things happened since then. But this is like a thought experiment, right? So for those of you that that are not familiar with it, the example or the experiment goes as this, right? So imagine I have like one of you that doesn't speak Chinese, right? Locked, not at all, not even like any other, like you only speak German, right? Or only English. It's like you only speak English. I'll lock you in a room, right? And you're in this room now, and you have all the knowledge that there is, like everything available in books around you, right? But they're in Chinese. So you don't actually know how to read them at all, right? So there's no translation. It's all pure Chinese. And you're sitting in there, you have no idea about Chinese, right? Now there's somebody else, me, for instance, putting in questions through the slit. You don't have any access to the outside, right? Like I put questions through a slit. The questions are in Chinese, right? So like you don't know what to do with this question, but you have all of the knowledge in the world at your disposal. And the only thing that you do is you basically look up whatever symbols you have in front of you, look through all of this knowledge and see what corresponding answer or symbols there exist to this question, right? So basically look up like all of the like Chinese symbols, right? And then you basically check basically what the answer is, write it on a piece of paper without understanding what you're writing and throw it through the slit back out. So from the outside, for me, it looks like there's something intelligent in there that offers any answer to any question I could potentially ask, right? Now, where's this intelligence, like this basically like this emerging intelligence coming from? The books are just books. There is no intelligence in the book, right? Well, you get what I'm saying, right? Like there's very intelligent books and there's a lot to learn by reading books. So please do read books, right? But still, right? So there's no actual agency in the book. And the person, you in this case, right, doing this has no idea what they're doing, right? They're just looking up symbols, like in copy pasting them. So I would argue that's not an intelligent action either, right? So why does it seem to me like there's somebody super intelligent in there? Or where is the intelligence is usually the common question.
When you ask why does it seem to you as though people were intelligent? Well, you put a question there and you get out the right answers from there.
Okay, no. You're correct. I kind of like gave it away already. But like, yeah, where is the intelligence in that room, right? In the whole process, where is the intelligence?
The people that wrote the books, I guess.
Yeah, but they're not in that room.
Yeah, there is no, but after that, there is none, except from your interpreting these symbols.
Yeah, I mean, the whole experiment basically goes in the direction and showing that the definition of intelligence is not even that clear, right? Because like as I gave away, unfortunately, my question is like it appears to me as it is intelligent, right? Doesn't mean that there is intelligence in there, right? So that kind of thing. But yeah, this is the questions. Are LLMs basically just Chinese rooms, right? Like that's kind of what they're tackling here, and they kind of want to address this through like querying or like through asking LLMs to do certain things, right? And there's benchmarks, right? There's like things like addition, code execution, code generation, like drawing things through SVG, for instance, right? Like these kind of things, right? So in total, they like look at 11 tasks, but they don't just do this vanilla benchmark tasks, but they actually provide counterfactual versions of that. So they do addition, but not on base 9, instead on base 10, right? You do Python, but every list begins with 1, right? Like you draw an image, but you draw it upside down, right? You play chess, but you change the configuration, like the configuration, the board looks different, right? So like all of these are basically what if questions, right? So what would the answer to this equation look like if it would be in base 9, right? And the idea there is that like an intelligent or somebody that like would be able to reason, right, would be able to understand what we asked of them, right? And they would provide then the correct answer. Make sense? So this is basically what they did. And just to give you some illustrative examples, so in terms of drawing, right? So the idea is that like those are like different like commands basically they should consider, right? When drawing it, like so basically they say like, oh, hey, draw me an image of, let's say, a unicorn, but consider that I'm gonna v-flip the entire image, right? Like a v-flip would be an SVG command, right? And then it says, oh yeah, in this case, that's what a unicorn should look like, right? And it's obviously wrong, right? Like it's, I mean, that's not a unicorn. That's clearly I don't know, like a snowman that had too much parrots. I don't know. Anyway, so like, yeah, you can see like all of this basically at some point messed up. And this was GPT-4.0, I believe, when they did this, right? So like arguably even one of the like better models these days. So yeah, does that mean that basically they're just lookup tables? I don't actually think so, right? So there's like they're not completely useless in this sense. So for like some other additional examples, right, we actually can see something somewhat reasonable. For instance, over here, right? So if we say X or like corgis are mammals and mammals are animals, are corgis animals, right? And now we do something. Okay, what if corgis are reptiles and reptiles are plants? Are corgis plants, right? So like all of us would agree, yes, in this case, corgis would be plants, right? And as a vegetarian, I should be allowed to eat that, right? But like again, this is counterfactual, right? Like so, this is not like real, but still, in these type of logic quests, like the LLMs perform quite well, right? Again, GPT-4, I believe. Whereas in other like arithmetics, they kind of suck, but to be honest, they kind of suck to begin with. Like they're not that great either, right? Yeah, and with this, we're done for this part of the lecture. So if you have any questions, if not, we're gonna directly dive into the 5 and 5. So this was a bit of a longer lecture, right? But we decided to only do 2 this before lunch break. So we do 5 and 5, and then we do lunch break. Okay.